Hi all, in this video I'm going to do Poisson regression or count regression using Julia, and in this video I'm going to show how we can use the UK football data or English Premier League data, because we have seen in the previous videos that English Premier League data, the home team scored a number of goals, and if we want to model number of goal, it will be either through a Poisson regression or negative binomial regression. So what I'm going to do in this video, I'm going to show you how to do Poisson regression using Julia. Okay, so first in my Jupyter I'm going to start a Jupyter notebook. So first I will give a title to my notebook. Say Poisson regression using Julia. Okay, and then the first thing I'm going to do, I'm going to call CSV data frames and CRRao. These three for sure. Let me run this. Now in the same folder where you are starting your Jupyter notebook, I have downloaded 2021 data and 21-22 data. So I'm going to use 2021 data. Okay, so what I will do, data frame CSV dot file, quote unquote. I just need the name. So file name, you keep the file name in the same folder, so that will be helpful. Okay, so this gives me the data set that I'm looking for. So there are 380 games are being played. Okay, and there are 106 columns are there, so there's lots of columns are there. Okay, and now what I'm going to do, I want to model number of goals scored by. So if I just go back there and if I note.txt click on that, so I want to full-time home team goal, that is FTHG. This is what I want to model. Okay, so what I want to model is, the model is, okay, first is, let me just at least write down few things. FTHG, these are the basic definitions. Let me just copy it down. Okay, these are the variable definition. Okay, variable definition. Okay, and then I will just copy few more things. Attendance, all these informations I am going to. Okay, and some of the betting statistics as well. Okay, oopsie. Alright, so let me just stop here. So these are the, so now FTHG is the one of the variable here. FTHG, this is the home team score, basically full time, how many goals scored by the home team. So this is what we want to model, and we want to model as a function of what? We want to model it as a function of maybe home team, how many shots were taken by the home team, and like HS, and how many shots were taken by away team. Okay, and then how many home team shots on target. Okay, and then away team shots on target. Then home team corners, how many corners were taken by home team, away team corners. And then maybe bet 365, the scored by bet 365, and away teams score. All these things we want to model. This is the model that we want to model, but the home team is, so model, this is my model, this is the model that we want to fit. Okay, so this is, so effectively this will be like Poisson lambda Poisson lambda, and then log of lambda MBDA lambda equals to beta naught plus beta 1 HS. So this way beta 2, beta 3, beta 4, beta 5, beta 6, beta 7, and beta 8. So this is pretty much what we have. Okay, so let me not take dollar here, so maybe I'll just put it like this and put it like this. Let me run it. Okay, yeah, so maybe I'll just put, yeah, if I just do this, probably this is will make, okay, so maybe I'll just put begin equation array EQN ARRAY and end EQN ARRAY, and it will work. Yeah, so this is what the model I want to fit. And so for that I'm going to call CRRao, and the first model that we are going to fit is fit, okay, at the rate formula. Okay, and first is FTHG, and then HS plus AS plus HST plus AST plus HC plus AC plus B365, oopsie, 365H plus B365A. Now after that I have to give the name of the dataset df train, okay, and then I have to give I have to say the class of the thing, but X. So maybe I'll just CRRao package. I'll just go to the develop package. So API reference Poisson regression. What I will do is what I have to do. Yeah, so Poisson regression, that is what we have to do here. So Poisson regression. So if you write POI and then tab, it will fill it up for itself. Now if you just do this will fit a maximum likelihood estimate. Okay, maximum likelihood estimate, or MLE estimates. Okay, let me just put it up there. Yeah, and now let me just run this. Why it is not formula? Okay, so I have to call stat models. Yeah, stat models I need. Yeah, so yeah, I think now it is fine. Okay, so if I look into it, HST, home number of shot on target by home team, going to have a very strong effect, positive effect. Obviously, more shot you have on the target, the chance of having scored is high. And then this is another home team now shot and has an effect. And then this is also home team number of corner by home team. And what is the Bet365's odds for the away team? That also playing important role, and you can see that this coefficient has a positive effect. All right, interesting phenomena that we are getting. Now suppose we want to predict, suppose we want to fit a Bayesian regression model, Bayesian Poisson regression model with say Reach prior, Bayesian Poisson, Bayesian Poisson regression with Ridge prior, RIDG, Ridge prior. So if I just run this, so if you just go there, all I have to do is essentially just copy this thing, and obviously now I want to change the name. Maybe I will say Ridge, and after the Poisson regression I would say prior Ridge, and if you just prior _r and then if you just tab, it will take the rest of the thing. Okay, so you don't have to really worry about that. Let me just put it here so that it is kind of aligned and you can see the entire model. So let me just run it. So if you look into by default it always simulates 1000 samples, and if you look into the R hat, you see the R hats are all close to 1. So it took 500 burn-in, and after that it simulated 1000 samples after burn-in. It is very fast because it uses Hamiltonian Monte Carlo method. And these are the coefficients estimates. So here you have 1, 2, 3, 4, 5, 6, 7, 8 coefficients and intercept. And now here also, so total 9. So you can see there are 9 coefficients, including first one is the intercept, and lambda is the scale parameter that is required. Okay, so intercept is negative 0.35 in MLE, and we are getting slightly off here, negative 0.6. Others are like negative 0.3 for HS, negative 0.3, negative 0.2 for, yeah. So the other values are looks like 0.238 for HST, which is 4th coefficient, 0.22, yeah. So the coefficients looks like similar to close to that of MLE, but it's very simple. If you want to see the detail of the reach prior, I think you can go to the guide, API references, okay, general interface, and then prior distribution. So the first thing you can say prior Gauss, and then here is the reach prior and all the definition of the reach prior. The way it is written, we have taken an appropriate distribution, which means Poisson, then you just take the Poisson and automatically it will do the rest of the things. So this is the reach prior, the way it is defined in CRRao. Next, we can try Laplace priors on the beta. Laplace distribution are being imposed, and inverse gamma prior is being imposed on the Poisson regression. So if I want Poisson regression with Laplace prior, you can plot very easily using CRRao. So Laplace prior, all you have to do Laplace prior. Oopsie, sorry, I have to do a mark down. Okay, now it is fine. So Bayesian regression with Laplace prior. So all you have to do is just copy this guy. So now on the coefficient we are applying Laplace prior distribution on the coefficient. This is typically so you just change the name of the prior plus, and it should and run, and CRRao will understand automatically that okay, this is a Laplace prior that the user want to apply, and boom, it runs and it gives you the all the estimates. So by default it will simulate 1000 samples after 500 burning. So from 501 to 1500 iteration is being reported. R hat are all close to 1. So this is a good news. That means the chain has converged, and you can see similar kind of things, behavior you can see. Okay, so this second coefficient was HS is effective, this is strong effective. The fourth coefficient was my 1, 2, 3 for HST is strongly have strong effect, and but the last one here it's saying that the odds does not have any effect. The odds does not have any effect. The sixth one is I think it was corner. 1, 2, 3, 4, 5, 6. Yeah, corner does have had an effect. Yeah. So Laplace is saying that in the MLE we got 3. In MLE method we got 3. At a 5% level we can say home shot, number of shot taken, number of shot on target, and the bet 365 is odd for away team. But it was surprising that I would not expect that it will away teams odds will have now effect on number of goals scored, and Bayesian methods is actually rejecting this method. I mean saying though reach prior says yes it did indeed, but Laplace prior is saying no, we are not. So this is important that you apply different kind of models and then you compare the results. And then next we can try Cauchy prior. Okay, so again very simple, fitting Cauchy prior. First we will give a name. First we will put it as a markdown, and then say instead of Laplace we see first Cauchy prior, and then what we are going to do is simply plot, just copy this guy, Cauchy prior, and instead of Laplace just plate C and then tab. It will fill it up by itself and then run. So while okay, it was very fast, it was very fast. So, and it is indeed all converged as usual. The R hat is all close to 1. So this one has an effect, strong effect. This one has a strong effect. The entire 95% confidence interval does not include 0, and the last one also has a strong effect. This does not include 0. Sixth one, the corner, also has an effect. So corner, number of shots on target, number of shots on target, number of corners. These are going to have an effect. The model is again and again saying, and the odds of the away team by bet 365 seems like having an effect. Not maybe strong or something, but it seems like it does have an effect. So what is Cauchy prior? Let us see the Cauchy prior. In the everything of the model is same, but on the beta and alpha, on the coefficient we put Cauchy prior with a scale parameter have a half Cauchy distribution. So this is very robust prior. And next what we will try T distributed prior. Okay, so here we are going to scaled T distributed prior on the beta and alpha, and on the scale we implemented inverse gamma prior. So very variety of prior options we have in the CRRao. So what we are going to do next is T distributed prior. We are going to implement the T distributed prior. Okay. T distributed. Okay, just you write T and press tab and that should be fine. It's very fast, looks like. Sometimes it's a bit slow because T distributed might take a little bit time. Okay, let us see. You see, T distributed prior did not able to converge. You can see the R hat are 2 near 2, so that means definitely these the algorithm quantum Monte Carlo did not converge by the 1000 samples. We need to increase the number of samples. So, and you saw it is slow, so I'm not going to again increase the samples and run it, because it will just take time. All you have to do just increase the sample. I can show you. All you have to do just probably you just put 0.95 and then you have to, instead of 1000 you have to just set 10,000 and run it. but I'm not going to do that because it will just take longer time. So you try it yourself, but I'm going to try another prior which is very popular prior called horseshoe prior. Okay, so let me try horseshoe prior. And horseshoe prior is, let me show you how the horseshoe prior works. So this is the y follow proper distributed, typically in natural exponential family. In our case it will be Poisson with mu I, and so mu I will be alpha plus xi transpose beta, and on the beta and alpha there will be a conditional normal distribution, and on the scale parameters of the conditional normal distributions we will have half Cauchy distribution. So it's interesting, it's a scale mixture distribution, and it's very nice. It's very popular in the Bayesian literature. It has lot of good properties, lot of good horseshoe prior. Okay, so let me just run it. Oh, I have to call it markdown and then it will run. Yeah, and then now what I will do, I will just copy this. So what we found, the t distributed prior will always require a bit of more samples, and then so h is, I will just say, and so I don't need, I will just use the default, and h and then horseshoe will work. Let me just run now. Okay, it was reasonably okay. Let me see if it was converged. Yes, you see it did converge. It did converge, and the way it has been horseshoe prior works is for each beta I there will be a local scale distributed. So now you can see that so this is, so that means for each beta 1 there will be a lambda 1, beta 2 there will be lambda 2, and beta 9 there will be a lambda 9, and then these are the local shrinkage parameter, and tau is the global shrinkage parameter. So all these parameters makes interesting local shrinkage and global shrinkage, makes the horseshoe prior very attractive to the Bayesian community. And what happens is, what we see, this is the intercept, then next is the HS, the home team shot on target. We see this is fully negative, all the entire 95% confidence interval. Then this is number of shots on target is completely positive, and this is number of corners completely negative. If you get too many corners, your number of goals scored will be less. Somehow corner has to do with the negative, something to do with the negative. And what we are seeing that away teams and the bet 365 does not have the odds does not have an effect by horseshoe prior. So what we are seeing according to the model of, so we can safely say HS, which is home team's home team shot, HST home team shots on target, HC that number of corners by home team. These are the three other sort of for sure kind of model. So we can, what we will try a slightly smaller model. Let us try a smaller model, and just home team shot on target, home team corner, number of, okay, so that's how. So now we have a shorter model, and let us run this. So it will be faster, it was faster, yeah. So we can see that each of these parameters were quite fast. And now what I'm going to do, we are going to just say predict if I just say predict, you can just use these models to predict also, and then you give the model and give the data set name. So the data set name is here I'm using train. You can have a test data also. So if you just give us a predict FTHG, right? FTHG, and if you can see, so you can see that they are giving you the prediction also. So this is one of the advantage of CRRao. You don't have to, you can fit any models and you can get the prediction also right away using just call the predict functions, and it will be done. So this is how you implement Poisson regression using Bayesian prior. So Poisson regression, both likelihood and the methods and the Bayesian implementation of the Poisson regression with Julia. So let me just write likelihood and Bayesian Poisson regression using Julia. The number of implementation that we have done: likelihood, maximum likelihood method. So actually we use Julia and CRRao, okay, and then we used reach prior, Bayesian reach prior, then we used Laplace prior, then we used Cauchy prior, then we used T distributed prior, but it was not very successful. It did not converge nicely. We had to run more samples, T distributed prior, and finally horseshoe prior. So all these we implemented very nicely and using CRRao in Julia. So I hope you enjoyed this video, and we will continue this in the next video. This next video we will be doing negative binomial regression. Thank you very much.